Earlier, we saw the intuition behind one transaction and one value. Now, we're going to discuss how to extend it and generalize it into an algorithm. First up, some terminology. First, flushing to disk. For logs, it implies appending to the log disk. And for regular data pages, it's writing it to disk from RAM. So this is the difference between writes versus appends. One with access cost and one with zero negligible access costs. But both are referred to as just flushing to disk. Next, see the update record. That's also known as the undo logs. Will typically have all the transaction ID, the information about the value we're changing, the old value and the new value. So update record, also known as the undo logs, that's a list of update records that we have within a transaction. When we have multiple transactions and multiple values we're updating, you can see how we can use the same update record with just different values of transaction ID and the value that we are modifying. So this pattern works well for extension to multiple transactions and multiple values. Quick reminder, if you have the old value and the new value for every item you're changing, then you can go back and forth in the transaction. That is, you can commit the transaction or you can undo the transaction or abort the transaction. That's the core idea behind these logs, undo and redo logs. Finally, when the transaction wants to commit, we add the additional commit record in logram, which is eventually flushed to disk when the transaction commits. What does a transaction commit mean to the database? First, it will take all the update records and the commit record and will flush it onto log disk 1. At that point, it knows that it's committed. And then it notifies the user or the application that the transaction is committed, and moving forward, the transaction is done. Until that step, the database could always just abort or commit and roll back and tell the user to redo the transaction from scratch again. But after the commit record and the log update records are on log disk, the database is fully committed. That's the definition of a commit from a database's perspective. We saw the intuition behind one transaction and one value earlier. For big scale, what do we have to work with millions of transactions and millions of data pages at the same time? So what if there is no more space in log RAM or in RAM for all our update records? It's a common problem with big scale transaction systems such as stock market transactions and also with consumer applications dealing with large scale user data. And they have memory constraints with like billions of updates happening and also time constraints, transactions that span multiple hours or even days. Well, the good news is that we already have the necessary components to make this scale happen. So we already have our log disk. So the only change we need to do is that we can also append partial results of transactions onto log disk. That is, we could use the same log disk for undoing partial transactions. And we therefore are using our log for atomicity in addition to durability. Programmatically, what this means is that the update log records can be written from log RAM onto log disk even before the transaction is committed. And that's a small change, but actually has a huge improvement on performance. And intuitively, we have information on the update records to go from old value to new value, of new value back to old value in case of an undo. That's the intuition, but let's now formalize this in what is called as the write-ahead logging protocol or the WAL transaction commit protocol. As a quick reminder before we dive into the actual WAL algorithm, we're focusing on durability and atomicity. And also the transaction is committed once the commit record is on stable storage, so disk or any non-volatile storage device. Let's dive into the algorithm. So for each tuple update, we will write the update record into logram. We've seen that earlier. Next, there are two rules for flushing for the log. Let's start with rule 2 first because the more natural one, and then we'll switch to rule 1. So rule 2 says that before the transaction commits, as we've seen in the prior examples, we have to flush all the update records to log disk and also flush the commit record to log disk. This is what we'd seen in our prior examples even with one transaction and one value and also with multiple values. The idea again is to make sure that we have enough information in the log disk to undo or redo if the system crashes later as well. Rule 1 is about data pages. So before you write a modified data page on disk, Rule 1 says that you have to flush the update record into log disk. That is, you have enough information about the old value and the new value to undo, redo if the transaction later aborts. Notice that Rule 2 deals with commits and Rule 1 deals only with modified data pages. This is an example of an asynchronous algorithm. That is, different parts of memory can do different things based on specific rules. So what happens to the log and data pages, they're partially independent of each other. It's often intuitive to visualize as dependency graphs. So as an example, Rule 1 for each tuple update, before a data flush, the database must flush the update record for that specific page onto log disk, sometime earlier, not right away, but sometime earlier. And Rule 2 is for commits. Before the transaction commits, let's focus on the flushing commit record to log disk in the green box. First, you need to have flushed all update records to log disk before you flush the commit record to log disk, because that signals the end of the transaction. And you can see that in the arrow between the yellow and the green box. Now back to the green box, the transaction can commit after the commit record is on log disk. The WAL protocol is one of the simplest and most popular logging protocols. Now let's run through an example with the WAL protocol. So what we're going to do is we're going to look at data records in memory and disk, and also logs in memory and in disk, that is logram and log disk. Also, we have Rule 1 and Rule 2 at the bottom of the page for a quick reminder. Consider rows A and B in two separate I/O blocks. On the left column, notice that we're going to run through an example WAL sequence. So we're going to run through start transaction, and we're going to first read A and read B. That's R of A and R of B, and then W of A and W of B for writing A and writing B, and modifying it from A to A prime and B to B prime. So nothing new so far. All we're doing is just reading it from disk into RAM and modifying it in RAM. Now we'll start one WAL sequence. Later we'll verify that it is indeed WAL compliant. We write U of A prime and U of B prime into log RAM because the A prime and B prime have changed. We use U as a short form for update record, for which keeps the old and new values as well as the transaction ID, as we saw earlier. Sometime later, U of A prime and U of B prime are flushed onto log disk. Later, switching back to the data records, A prime is now flushed onto disk, B still stays the same. Later, the transaction commits and the records are flushed onto log disk. And later, B prime is also updated on disk. This is an example WAL sequence. Just to verify, let's just ask a few questions so we understand this material. First question, can A prime be flushed to disk before U of A prime? No, absolutely not, because of Rule 1. Because Rule 1 states that the data flush or A prime flush has to happen after the update record is flushed to log. Question 2, can A prime be flushed to disk before the commit record? Well, let's look at it visually and then intuitively. So data flush is in the yellow box. There's no dependency between the data flush and the flushing commit record in the green box. And intuitively it makes sense because before A prime is flushed, U of A prime is already on log disk, which gives us enough information to undo or redo as necessary. Well, question 3, what about B prime? Can it be flushed after commit record? And the answer is yes. And again, it's because U of B prime is already on logged disk. That's a lot of dependencies to keep in mind. And thankfully, the database will hide this complexity for most of the data practitioners and make it easy with just using simple transaction blocks. As a cs145 student, you need to understand how these blocks work and how to make changes as the underlying systems and needs evolve over time. Let's consider two scenarios. Case 1. System crashes before commit record is flushed onto log disk. Then the system aborts, notifies the user, and then as part of recovery, will fix A prime using information from U of A prime, which is already on log disk. Case 2. System crashes after the commit record is flushed onto log disk. Well, in this case, as part of recovery, U of B prime would be applied and B's value would change on disk from B to B prime. A prime has already has been updated. Well, that's it for logging and write-ahead logging. WAL is powerful and is general and helps us address the questions we started with, which is how do we handle big scale in terms of transactions? So billions of updates or transactions that take very long. With WAL, we now have the flexibility to add to the same log disk information about partial transactions, and so the undo and redo information, and so we can use the log for atomicity in addition to durability. And we achieve that by just two rules in when data flushes can happen and when the log flushes can happen. It's tricky stuff. To reinforce, I would recommend replaying the video, turning off the audio, and see if we can retrace the different steps. Also, we hope the mega thread on Ed will be useful for questions, clarification, and trying out variants. Good luck!